started to distinguish between the network on not working so well. On the previous slide, where we said this is kind of a network where we have current and anomaly set, because from the context that is a network of email accounts, and we would expect actually a lot of nodes to participate in the communication. And now the question is about this network. And what would you say here? Could you think this is already an anomaly state if you think how, in general, the network could evolve, also with the background that the nodes are countries? Also, maybe you can spot already another difference here. We have some edges which are thicker, some edges which are thinner. And that's what I want to draw, like this contrast between these two networks. This is actually a network of scheduled commercial exchanges of electricity of countries. And actually, this is a state we would kind of embrace, because you see all the countries are connected. So that is a good sign. There is no one like left out on the market. We also see some more or less expected behavior, right? Germany, Austria trading a lot, or like France, like big clusters also in energy production and trading. And you see like how different those two contexts are. And that is where we come and say, okay, we have in general this statistical field like process monitoring, right? It's where we want to look at the process and understand whether it evolves optimally. And the goal is basically to detect anomalies. But with the networks, we can think about like its structure, where the anomalous behavior can happen. Or imagine now, like on the last slide, you saw a network which is completely connected. So we don't see this kind of random behavior in the edges. So that is a question: how can we then still enable the network monitoring where actually the structure doesn't change? And the three questions I would like to answer today is, first of all, why it can be challenging, like looking at such networks which have fixed structure, and in general, how can we then monitor them? What about already existed models? Because I'm actually not a really theoretical person, I'm more of applied person, and it's always interesting for me to understand what can we already take from the theory, from the models existing, bring them into the novel context and make it work. And then the third point is, what are the possible use cases, right? And here you already can notice this title part, Temporal Edge Network processes. We basically focus on fixed networks with something happening on the edges. So, and here are the three parts of the talk. First of all, we will define these networks, temporal edge networks processes. Then we ask ourselves, okay, how can we model and monitor such processes? And what about kind of empirical study? We will look into cross-border physical electricity flow. This is different from scheduled exchange, or like this trading I meant, because physical electricity flow is indeed like completely static, and it also behaves to physical laws. For example, you can notice sometimes countries have to surpass several countries. For example, you can't sometimes trade directly, let's say, Austria to Germany. You have surpassed some other countries just because of the flow of the law of electricity, how it flows. And that's why it's actually kind of a good example to monitor. Let's start with a broad understanding of what network monitoring means. And we can subdivide it into two types. First type is this something that I showed on the first slide. It's a random network monitoring. So you focus on the structure of the network. You can imagine like anomalous behavior in a social network, like in this email communication or something similar. And here the object of what we monitor is the network itself or its, let's say, adjacency matrix. And what we then perform is actually surveillance of networks. What we, however, focus today on is the fixed network monitoring. That is where the nodes and links are given. So we don't have some randomization in how the nodes are connected, because we have just a static structure. And what happens then is we either have to look on the node processes or edge processes and observe them over time and understand whether the network is still kind of in its normal state. And an example is again like this detection of flow deviation in it, for example, like electricity flow or like some internet traffic and so on. And here we would speak rather of surveillance on networks. So network is similar to, at least in the talk, I use it similar to the graph. And the definition of that we have the nodes and edges. And yeah, you can call nodes also vertices. And we call two vertices to be connected or like adjacent if they have a common edge. And to, let's say, summarize this information about which nodes are connecting which node, you would create an adjacency matrix. And here you would have 1 if there is this connection between two nodes, or 0 otherwise. In case you have a asymmetric adjacency matrix, then you would have, if in case you have a weighted edge processes, then you would have an asymmetric matrix. Otherwise, if it's just 1 or 0, then it's a symmetric case. And now we come to this definition of what temporal edge network processes are. Imagine that each edge has some time series on it. And the whole process then becomes, for a temporal edge network process that we then call X, and it's basically on the graph G. It has this assigned structure, a stable structure of the network. Here's the visualization of that. So what you notice first, these edges are the same as in the time point 2. The nodes are also the same. What is different, however, are the numbers, or let's say the flow intensity, let's call it like that. And here in time point 1, for example, you can notice, okay, the flow between purple and green was 5 and then it becomes 3 and so on. And that's the only information we have, right? And the goal is to understand, is it still in its, let's say, normal state, or something starts happening? And now thinking about what are the matrix challenges is, first of all, just look into the field of network monitoring, or in general, network analysis, specifically from the statistical point of view. All of the attributes, or like variables that you attribute to nodes and edges, usually regarded as some kind of extra layer, or like, yeah, let's say additional or aid information to understand the whole network better, like edge likelihood. So it's not really ever was so strongly treated as the main focus of network process. And that's basically that field focus is more on these random models or random network monitoring, where you have the models and yeah, trying to understand the edge likelihood and not so much of what exactly happens on the network. But there are also the reasons why it might be the case, because first of all, if you now think about this edge processes, you have to think of how can you model the interflow dependencies, right? Because one flow might depend on another flow. So it has to flow, for example, I don't know, if you think about rivers, right? They start in one country and then in another. So it actually kind of depends, right? Which country it passes, how much water it kind of delivers from one point to another. And this is interdependence is challenging to preserve. Another point of view is like, if you think of nodes and edges as the different context parts, edges actually involve pairs of nodes, right? It's not just one node, it's actually a pair. And then as I said before, like if you then think about these interflows, and it's actually even several pairs of nodes that start kind of depend on each other. So that's the question, how can we also treat that way? And this representation shift should also occur in all adjacency matrix or in or structural understanding, right? How can we model it so that these dependencies are still accurately preserved? And this is where we basically have to say, okay, we truly need some new monitoring method that can focus on this kind of temporal and contextual changes on the network and not just off the network. If you have questions, you can just ask by the way, right? Yeah. So now thinking about what I said on the previous slide, we now don't have the interest just in the single nodes, but we have the interest in the pair of nodes, right? Because that's exactly what forms an edge. So you can think about, we could then convert these edges to actually new nodes, right? So you can imagine now this pink and blue connection, like this edge becomes an actual node that has a value 6, right? Like has this weight 6. What is unclear for is how can we connect this new structure, right? Because there is currently we can't just randomly start thinking about, like, we can, let's say, take from here something else, the information that could help us. And there are several ideas how we can proceed. First is just to place these connections randomly, like using the already established random network models. For example, edges training, you just choose a number of edges you would like in the network, and then you place them randomly. So it's basically a good idea if you have no clue about what is actually the structure should be about. If you, however, have a little bit of knowledge and can understand which nodes should be which flows should be connected stronger and which not, you can think about using stochastic block model. That is where you generate the clusters, right? So some inter communities, or like some communities, can be have a more intense connection, other less intense connections, and that is very effective when you know, like, there should be this kind of partial groups in the network flows. Or you use a different procedure where you say, okay, I would like to have a deterministic construction. And one of idea is to just look in what exists in the graph theory, and you will quickly find this concept of a line graph. And that's basically where you convert nodes to edges, and then you connect those edges which have originally a shared node. I will show in a second what it exactly means. What is great about that is, first of all, you bypass this kind of a random effect, especially when it doesn't make sense, like in some geographical sense. And you also preserve some, like, connectivity constraints, right? Especially the ones with the locally, right? Because you just create the connection between the flows that are definitely adjacent in the original graph. So this is an idea if you just have 10 flows and randomly create with the edges training model the connections, or you take the stochastic block model on the other side, you create these two kind of clusters and then connect. And now this idea of having a line graph. So line graph or edge to vertex dual graph basically does the following. You can see that the letters placed on the edges, and these letters become actually the new nodes. That is something what we just already saw on the previous slide. What is new, however, is how we connect those new nodes. Like, let's call them still flows, so it's easier. So how can we connect the flows? We connect the flows in the case that we have the common node originating. So as you see, this flow flows between 1 and 2, and then the flow C flows between 2 and 3. And these A and C are now connected. And that's how you proceed. So this idea, as I said, can actually well preserve some local constraints, and it also makes it very straightforward of kind of, there is no factors or parameters you have to select to otherwise create these randomization connections. So this idea is something we'll also use in the empirical study. And now you can imagine what we can have, basically how we can invert the previously process on the edge networks where we don't have the conversion to, like, this is the original case, right? You have the original edges, how we can convert them first to these nodes, and how we can connect them together, right? So this is basically, let's run an example. Orange and pink have here the node, and orange and pink is a common node between this edge, so there is weight 6 and with the weight 14. So 14 and 6 should be connected. Statistical network monitoring now can then be subdivided into the network modeling part and the process monitoring. There are different ways how you can perform the process monitoring in general, like data-driven, for example. We decide, however, for the model-based monitoring approach, and this means we first need to select a suitable model to actually, like, model this new representation of temporal edge network processes. For that, we have to think about what actually the alternatives are. First of all, it could be some models for processes on networks already, like where you can also think about, like, Poisson processes and so on. In this direction, you can think of random walks on stochastic temporal networks. Non-Poissonian processes also exist, volatility models on networks. What we go for is so-called generalized network autoregressive model, and that will be explained in a second. And now the second part of the model-based approach is what and how we monitor. Like from this model that we took, what can we take further and how we perform the monitoring. What we do is we compare the results obtained by using this model to the actual case, and we retrieve from them the deviance residuals, also called forecast errors, right? So you have the model state, you check whether, let's say, one edge by the model would have the, like the flow would be 14, and actually today it's 10. So the forecast error or the deviance residual is 4, and then you start monitoring, right, like this, this value. And which technique is then suitable to perform the monitoring of this deviance residual of the forecast errors are the control charts, like one of at least which happens to suit well. So let's come to the first part, is how we model. So now we have the idea of, okay, we inverted or graph so that the flows are actually nodes. And if you look into the space of what was already developed for the actual nodes, we will find this model, GNARX model, or GNARX, if you include also some covariates, which has the focus on the node-specific regression. So consider we have now this multivariate time series, right? Like multivariate because each variable is basically one node, or like one flow in all cases. And the number of, yeah, exactly, the number of nodes is basically the number of time series that you have. We can also include some additional regressors with denoted with the variable z. And then the GNARX model is basically a linear regression. I know it looks kind of with a lot of variables and letters in it, but it's basically a linear regression. Like if you think as it's like alpha times x at the time point t minus the log plus beta with some kind of a weighting effect times again the x part and then the rest of the regression. So it's just a complex way of representing it because we have this additional part of the network, like we will now see this is a beta and the omega, like the weighting. We have, of course, also the temporal correlation we need to include for with the regressor part. We can also think about there some lags we need to basically account for. And now the question is which flows actually depend on each other, right? And for that, I will quickly show the next slide. This orange flow has, first of all, first degree neighborhood, right? We would call it the first stage. Then it has the second degree neighborhood. Basically, this second degree nodes is the second stage neighborhood. And what you basically can do is here include this neighborhood stage of estimate more, like you would need to estimate one beta times the number. You basically loop it over the whole the stages. We, for example, in the empirical case, just concentrate on the first stage, but you can think about that doing also for the second stage and so on, right? It just depends on the context of the of your application, whether it makes sense or not. So once again, you then define what are the first degree neighborhood, second degree neighborhood, and so on and so on. And for that, you then also extra estimate these beta coefficients. And here you have also this weighting. I don't want to go deep into that, but this weighting basically shows how strongly this should be account for, like, of course, with the additional stages, you will expect like also a smaller weighting factor, and that is basically helps you to also in your neighborhood kind of correctly assign this strength of how the edges should be account, like how the flows are interconnected together in this sense. And now, after we select the suitable model, we'll come to the part, I hope, of how we monitor that. If you think about like hypothesis tests we want to perform, we can formulate it as follows. The zero hypothesis is about the observed 10 process, so like this temporal edge network process, coincides with the GNARX model that we have fitted on this process versus this alternative hypothesis. It starts deviating, or it basically doesn't coincide in anymore with that. And what we can use for that is technique from the statistical process monitoring that is focused on finding this change point, or basically finding the point when we rejected the null hypothesis, and by that show that there is something in the process happening that we have to investigate. And one of the ideas, like suitable part for that, is the control chart, and the control chart has a task to basically look at this process, compare to the upper control limit and the lower control limit, and decide whether it meets and now one, like hits one of these alarm borders or not. The question is here now which specific control chart to use, because there are several options. And for that, we can discuss the requirements we have. So the first requirement we want to satisfy is we don't want to think about where the change might happen, like is it a mean, is it a variance, is it something kind of a mix of the anomaly that can then be detected. And that's why we want a process that, or like a control chart that can have this joint monitoring. And for that is actually the residuals, like squared deviance residuals are very suitable, and we will see it in a second. And then also in realistic models or like monitoring settings, we have actually hundreds of flows. It's not just these little networks I'm showing, like these 5-10 flows. And here actually control charts should, or like might start having problems, because usually you don't expect, like in the multivariate control charts, more than 10-12 variables. Then you need to do something like this PCA, but then you lose the actual interpretation about which flow should I look at, like, and what should I fix. So this is why we first can think about detecting local changes. So basically implement a lot of univariate control charts and check if the flow is still under like this control or not. And then we can combine these local changes to so-called global change. And for that, we also need to understand, okay, how can we aggregate them? So this is a two-step process we now need to decide for. So for the first step, we decide to detect the local changes using the traditional CUSUM chart, where the statistic is based on the squared deviance residuals. And you see, I'm now starting using this iota variable. It basically indicates that we now talk about this inverted representation of the network, right? And there is a adapted test statistic from Grunti, where we can see like the length of phase one is denoted with M, then we have the K is the current time point, and B is the mean estimate of this forecast errors, which we computed in phase one. And this test statistic we can then implement in the control chart statistic to detect like when we have to flag the alarm or not. And in the CUSUM, you just need the upper control limit. So I just now didn't include the upper control limit formula. So this one you can find in the Grunti 2025. And you compare all this, okay, does the control chart statistic D meets or like falls below the upper control limit? If not, we need them to signal that there is an anomaly state. And if you think about how it would look like for just one of the flow, so it's a simulation where we increase the alpha parameter and run it, and you can see, okay, we have this detection delay like between the phase one and phase two detection, like when it's basically officially becomes out of control. And you here, of course, can see the actual timestamps like of this flow, because we haven't aggregated it yet. So it's gonna come in the step two. So now in the step two, right, you can imagine we have hundreds or like at least tens of such control charts running for each of the flow. So now the question, how can we combine it to detect a global change, like of the whole network? And one of the ideas is just use a threshold-based rule, like some kind of an expert-based definition of what the threshold is. And we have this n control charts, right, equals the number of flows. And we basically just create a cumulative change intensity function that collects all these signals, like cumulatively over all the time stamps in the phase 2. And as soon as one flow iota has a change or like has an alarm, we drop it from the monitoring so that this intensity function maximum can only be 1. So all the, like, because we normalize it here by the number of flows. So the total number of changes is basically the total number of nodes we have, or like of the flows. And by normalization, we can expect this maximum to be just 1. And for empirical study, for example, we set it to 0.2. So it's gonna be around kind of 16 flows in the empirical case that needs to flag so that we say, okay, there is an alarm there. Of course, it's like a very simple idea of how to aggregate it, because you can also think of weighting, like some particular flows that are very critical, or even just perform the whole monitoring on just some specific flows or like kind of clusters of flows. This is everything possible, right? But for that, you have to have like this deep understanding of what the actual process is. And here's this idea of if we combine everything, what like how could it look like the this in the simulation, right? In the simulation study, we had 500 iterations over 10 flows. So you can imagine here we basically on the y-axis just plot the mean cumulative sum of alarms, so like this mean value of the intensity function. And as expected, in phase 1, we have nothing happening. And then in phase 2, it gradually starts kind of producing the alarm. So like here is the average over all the iterations. We specifically don't set any threshold here because we just test like the whole kind of goodness of the approach. But you can also see maybe here a little bit this grayish part is basically how like variable the results for within the iterations, right? And these two lines show what are the differences between two parts. Like if you run it for Eldius-Riemann model, the connectivity model, or for stochastic block model where you set the alarms or like, the anomaly happen just in one cluster. And this of course would lead to the maximum value to be just the size of the cluster. It was half of the whole node, so 0.5 will be here the maximum, right? If you have equal number of nodes in both clusters. So that is the idea of aggregating it. And now we come to this empirical study of like the monitoring of cross-border physical flows, or let's say just of electricity. It's basically measured, you can see the text there, but what happens is like we just measure the electricity between two countries, exchange between two countries, and what you see here, you have a lot, or almost in every case, the parallel edges, right? So because there is some amount exchanges from Bulgaria to Macedonia and vice versa, just because it makes sense, like physically. And there's of course this strong cluster of Germany, France, Switzerland, and there's one more, I think, here around Spain and so on. So we have the weekly aggregation of observations, because actually you get our data, you can download it on the portal of the European electricity kind of platform, and we have to subdivide the monitoring into two phases. So phase 1, it's where we perform the modeling of the whole process, and in phase 2 we start, let's say, the actual monitoring and the proof of concept, right? Does the method work or not? What we expect to work in a particular kind of anomalous phases, something like Corona, start of the Ukrainian war, and so on. And as covariates, we have to, it was difficult to select something mean, just because again, you have to understand the actual base proton better, but we just took the amount of electricity produced with fossils versus renewables. And for us, the goal is to say the kind of approach works when it is able to detect the anomalous behavior during the period of corona pandemic and since the 1st of February. Why is a bit like the actual war started on the 24th. First is something like of preparation, we could think, right? Or like something already happening in Europe on the space. And now we come to this idea, right? We have like here already spot, right? We have so many edges now, especially given that they're parallel edges. Imagine them all converting into nodes, like into the actual network node. It's going to explode. Like there's going to be a very quick limitation of the approach actually not working for any kind of more or less real cases. So what we can think about is just actually aggregate these flows. So F1 can be the flow from, let's say, Germany to Denmark, and F2, Denmark to Germany. And now the question is, what are the options for us to aggregate meaningfully? First one is just the sum, like the sum of the flows in a Cox transformed way. Second is kind of two variables transformed with the box-Cox transformation, and then we take the difference of that because it can indicate some asymmetry, like you just look into asymmetrical behavior. And third is similar to that. We can also think if the flows are strongly different, then it's useful to use M2 or M3. This kind of strategies, because you can then see like the strength of this asymmetric behavior. M1 is good if you think about the flows being more or less the same, right? Because it's going to be difficult then to like, probably you're going to have a lot of zeros, like if not zeros, but like kind of static number in other term. So these three ideas we can test for performing the monitoring and for exactly us being able to then reduce the number of flows, like the inverted nodes, to just being like double as much. So in the actual case, then we had around 76 nodes or flows. Otherwise, we would have 140, like 150, right around that. And here in the representation, the size of the nodes just indicates how strong the electricity exchange is, and the color is a proportion, whether it's like more renewable, and if it's more renewable, then it's kind of around this light green, and if it's less renewables, then it's dark green, and if there is a missing data, then it's just blue. So this is a legend. Now we come to the first test of the monitoring statistic M1. And what you can see here, we have two periods colored. First one indicating the corona pandemic. Second one indicating the period starting from the February 2022. And what you can see is that the threshold, as previously noted, like by 0.2, so it's around 16 flows we would expect to produce a signal before we say, okay, something starts happening there. And what you can, of course, expect a lot of signals during the pandemic, then kind of, very light period of where nothing really happens. And then we start having interesting things. We, of course, expect between Russia and Ukraine to happen something on the electricity market or in general, like even on this physical level. But what's also interesting that Belarus and Ukraine also, like in about the same time, had a change there. And then we have some other, like Russia and Estonia, like all like these Baltic countries, they also had their kind of, the period of setting kind of the embargo and so on, like the sanctions and so on, also could be detected at the more or less correct time. And I think this one between Ukraine and Moldova was about opening actually new streams or something like that. So this was interesting that there are cases where we definitely can be sure that it's allocated correctly. With the pandemic, it's a bit difficult. We can just see, okay, that's expected, we're gonna have signals. What exactly, however, they should mean, this was, yeah, a bit challenging to research. So exactly, this was a monitoring of M2, and then you see completely different number of change points, and it exactly also different country pairs, or at least in some cases. So something again shows, okay, we have to think about which statistic to choose, because in M3, this is completely different to both of them. Like we get a new way of subsets, like which start triggering of flows, indicating like again, we would expect a lot of course, flows triggering in the pandemic. Something around Russia, Ukraine, Belarus should be expected there. But the challenge of what actually the best statistic is for all these, let's say, anomaly cases is, yeah, not so straightforward to decide. And that's why it's actually currently we are trying to understand how better to allocate these changes, because that's something also like from the, let's say, physical point of view, can we just justify there is some changes in the way how, for example, renewables are integrated and so on. Like, can that trigger actually some of the changes? So that's something we now look into. So the summary and the open questions are around, if we think about this procedure, we divided into two parts, right? We selected as a modeling the GNARX model, and we selected CUSUM chart to perform the monitoring, and that's basically created this procedure for yeah, surveilling tents. We have a strong current assumption around tents being just collected at the discrete times, but a lot of such flow processes are in the continuous timestamp. So that's the question, how can we extend to that, or can we extend to that? And when it actually starts being important to be incorporated, we went like to this weekly timestamps. That's why it's so far from being continuous, but actually, if we think about more realistic example, it should be there. Also, we have the assumption around the fixed structure, which is something we came from, so that is great. But what about if there are some, let's say some flows are deactivated, or there are some, yeah, just some differences in how the current flow structure looks like? How can we, like, do we need to completely remodel it? Can we remodel it when we start doing it? Like, given that some of the flows can even disappear. And also we assume GNARX to be a suitable model, like we could prove it with some standard statistics around like does the regression fits or not. But for all of the empirical cases, if you think it's definitely not just the one that should be there as a suitable one. So what are the alternatives? A lot of space open there. And of course, we showed this idea of aggregating univariate control charts or univariate signals into this global signal, but are there actually suitable multivariate monitoring tools? This is something we looked into, didn't, let's say, detected something very useful from the first point of view, and that's definitely something to look into further. So there are a couple of relevant references for those who are interested, and yeah, thank you for your attention, and I'm happy to answer more questions.